Today I'll be presenting our work, OPER, OPtimality-guided Embedding Table Parallelization for Large-Scale Recommendation Model. Deep learning-based recommendation models are widely adopted across various applications. Whether you are shopping online, browsing social media, or listening to music, the deep learning recommendation model will provide the content tailored to your interests. Due to their success in real-world application, deep learning recommendation models now consume the majority of data center computing cycles in industry. A recent report shows that Meta about 50% of the AI training cycles and up to 79% of the AI inference cycles are dedicated to these models. Although large language models currently attract much attention, DLRMs remain crucially important in industry. Before we dive into the optimization strategy, let's first take a closer look at DLRM. Typically, DLRM consists of three main components: embedding tables, bottom dense layers, and top dense layers. The bottom dense layers process dense inputs such as user's age. In contrast, the embedding tables handle the sparse input, which are often represented as a multi-hot sparse vector. And these activated entry within this vector are used to index and retrieve the corresponding rows from the embedding tables, converting the sparse input into dense embedding features. And lastly, the top dense layers utilize these features to perform feature interaction and generate the predicted click-through rate. What makes DLRM distinct from other traditional deep learning model is the use of the embedding tables, which introduce unique challenges when training DLRM or serving DLRM inferences. So typically, the embedding table in DLRM demands a large memory capacity. It accounts for more than 99% of the model parameters in DLRMs and can require up to terabytes of the memory. So as a result, it often takes a large amount of GPUs to training or serving production level DLRMs. And secondly, the embedding access frequency is highly skewed. It typically follows a power law distribution, where the top 5% of the popular embeddings account for more than 90% of the total embedding accesses. So this can easily lead to workload imbalance between GPUs, decreasing the training and inference efficiency. And lastly, the embedding table computation is sparse and input dependent. Unlike traditional dense models, where all weight has the same computation intensity, the embeddings used in computation depends on the given input batch, with only a small proportion of the embedding are accessed each time. And this sparse and input-dependent pattern presents challenges in distributed training for embedding tables, making it difficult to apply a standard parallelism method like the tensor parallelism. So to overcome these challenges, existing work leverages some coarse-grained parallelism method to train or serve the recommendation model. For example, the table-wise parallelism treats the embedding table holistically and trying to allocate an equal number of the embedding tables on each GPU. And the row-wise or column-wise parallelism equally partitions large embedding table into small embedding shards and scatter different shards to different GPUs. And lastly, the data parallelism will duplicate the embedding table to several or all the GPUs. And this parallelism strategy helps extend the large-scale DLRM training and inference to many GPUs. However, the granularity of this parallelism is too coarse-grained, and when dealing with the embedding table, which usually have a skewed access distribution, and this often leads to workload and communication imbalance between GPUs. To illustrate this, let's consider a simple 2-GPU case study. Here we have 3 embedding tables, and each marked with a different color. And each row within the table is an embedding vector, and the number in each embedding vector indicates the embedding access count, representing the popularity of each embedding. And next, we need to parallelize these 3 embedding tables across 2 GPUs, and each GPU have space for 7 embeddings. So first, let's consider table-wise parallelism. Due to the memory constraint, one table is placed on GPU 0 and the other two are placed on GPU 1. And this placement causes a significant imbalance in embedding table lookup workload and the communication between GPUs. And the lookup workload can be computed by summing up the embedding access count on each GPU and then multiplying by 2, since each GPU needs to look up the embedding for the other GPU as well. As we can see, GPU 1 needs to look up twice as many embeddings compared to GPU 0. Additionally, it needs to send twice as many embeddings to GPU 0. Next, we try row-wise parallelism. Each table is sharded into 2 partitions and placed on both GPUs. And this time, the imbalance is slightly lower than the table-wise parallelism, but the gap is still significant between 2 GPUs. Lastly, let's consider data parallelism. Unfortunately, this method cannot be applied since the memory on GPUs are not sufficient for data parallelism. So how to improve the performance? As we can see, the primary reason for the imbalance is the significant gap in per embedding access count. Therefore, we should consider a more fine-grained parallelism as a per embedding granularity. So let's try a fine-grained model parallelism approach by placing the embedding row by row. And this fine-grained model parallelism greatly reduces the lookup workload and the communication imbalance, narrowing the gap between the 2 GPUs to just 1. While this fine-grained model parallelism performs good, can we do even better? The answer is yes, since there's still some available space on the GPUs. So we can data parallel some popular embeddings by duplicating them on both GPUs to further improve performance. And by applying both fine-grained data parallelism and fine-grained model parallelism, we achieve a significant lower communication load. The key takeaway here is that both the fine-grained parallelism and a combination of data and model parallelism are necessary for optimal embedding table training and inference. However, achieve both requirements is not trivial. First, the fine-grained parallelism leads to a significantly large search space. There are n raised to the power of m possible embedding parallelism, where n is the number of GPUs in the scale of several hundreds, and m is the number of embeddings, which is at the scale of millions or even billions. Also, the problem itself is NP hard, so there's no polynomial time solution. And besides the embedded table placement, if we consider the optimization for communication paths of each embeddings, it will result in an even larger search space. And secondly, there is no efficient system for the fine-grained parallelism. Existing DLRM training or inference framework are designed for coarse-grained parallelism. If we apply fine-grained parallelism, the embedding table will be split into many small chunks across GPUs, which lead to many lightweight GPU kernel for embedding communication and complicated P2P communication for each chunk of embedding tables. So to overcome these challenges, we propose OPER, a systematic solution with OPtimality-guided embedding table parallelization. And OPER consists of 2 major components. First, we propose a heuristic parallelism algorithm to efficiently search for a near optimal embedding table parallelism plan. And second, we designed a distributed shared memory-based training system that efficiently supports the fine-grained embedding table parallelism. And our key contributions are highlighted in the green boxes, and I will introduce them one by one in detail. So to search for the near optimal embedding table parallelism, we first developed a theoretical performance model to formulate the parallelism plan and understand how parallelism influences the performance. The parallelism describes not only where the embedding is placed, but also the communication path of the embedding. So to formulate the embedding table parallelism, we use n times n binary matrix Pi to describe the parallelism for a given embedding EI. If Pi mn equals 1, it means GPU m will get the embedding EI from GPU n during training or inference, describing the communication behavior of embedding EI. And the sum of the column represents the computation amount for EI on a specific GPU, it describes the computation. Also, if the sum of a column is greater than 1, it means the GPU holds a 1 copy of EI, describing the memory consumption of EI on each GPU. So by using this parallelism representation, we can comprehensively formulate the key performance matrix of the parallelism, including communication, computation, and the memory consumption. So now we can search for the optimal parallelism based on the formulation. A straightforward way is to go through all possible parallelism plans and trying to find the plan that minimizes the computation and the communication while satisfying the memory constraint on each GPU. However, this is infeasible since DLRM usually have millions or even billions of embedding, resulting in extra large search space. So even use commercial solvers, it could take several days to find an optimal embedding table parallelism plan at the per embedding level. So to address these challenges, it is crucial to reduce the search space by increase the parallelism granularity. However, there's a trade-off between the granularity and the performance. So we propose a heuristic algorithm to approximate a near-optimal solution by adaptively partitioning the embedding table. And this approach helps us find the sweet spot between the parallelism granularity and the optimality. And we first apply access and memory-aware partitioning, which divide the embedding tables based on the given bounds for access frequency and memory consumption. And this approach helps us achieve a balanced partitioning size and access frequency among all the small chunks of the partitioned embeddings, and which is crucial for avoiding imbalance in the parallelism. And next, we perform model parallelism to distribute all embedding partitions across all GPUs. Specifically, we separate all partitions into two tabs, access-bound partitions and the memory-bound partitions. And we then parallelize these partitions using a greedy approach with objectives of access balance or memory balance, respectively. And this helps us achieve a balanced model parallelism in terms of both access frequency and memory consumption across all GPUs. And after creating a parallelism plan, we evaluate the optimality of the plan using our theoretical performance model. And if the optimality of the plan is not good enough, we increase the partition granularity, and then we repeat the partitioning and model parallelism policy until we achieve a model parallelism that have balanced access frequency and memory consumption across all GPUs. And this backtrack search process ensures us we could use appropriate granularity for the embedding table parallelism. And after the model parallelism, we then perform data parallelism to fully utilize available GPU memories. We use different data parallel strategies for training and inference as they have a different communication pattern. So for inference, we simply data parallel the embeddings greedily to minimize the communication between GPUs, since duplicating embeddings will not lead to additional communication in inference. However, there's one aspect that requires particular attention in a multi-node setting. Since the communication bandwidth between GPUs is not equal, inter-node NVLink usually have a larger bandwidth than the inter-node networking. So when we duplicating or embedding from an inter-node GPU, we should update the communication path of this embedding to the inter-node GPU to reduce the inter-node traffic. And as for training, things change. Since data parallel can not always reduce the communication amount, as data parallel bring or reduce communication in the backward phase. So for example, if GPU 0 need to access embedding EI in a training iteration, if EI is model paralleled on GPU 1, it only has one gate in the forward for EI itself and one put for gradients in the backward during training. So while if EI is data parallel on all GPUs, we have no communication in forward, but we need to all reduce the gradients among all GPUs. So in this case, data parallelism will have more communication. So we apply data parallelism only to the hot embeddings with sufficient high access frequency to reduce the communication amount. Next, let me introduce our system level optimization. Here's the execution timeline of the existing coarse-grained framework, which utilize separate kernels and the collective communication for different type of parallelism. If more fine-grained parallelism is applied, this approach will lead to significant CUDA kernel and collective communication launch overhead. So to overcome this issue, we propose an all-in-one embedding table that maps all embeddings into a unified memory space. And this approach uses a single CUDA kernel for all the computation and communication. To implement the all-in-one embedding table, we map the embedding partitions into a distributed shared memory space, which is a symmetric memory space that can be accessed by all GPUs. And many frameworks support this kind of abstraction, such as NVMe developed by NVIDIA. And by mapping the partition into a shared memory space, we can convert the embedding index into an address in the memory space and use a single kernel to handle all the embedding partitions. As shown in the figure on the right, the addresses are decoded by kernel at runtime to identify the GPU ID and the memory offset, which then will trigger local or remote embedding lookup. And this implementation has additional benefits. The local memory embedding lookup and the remote embedding lookup are seamlessly overlapped with each other, greatly hiding the communication latency between GPUs. And here is an illustration of the execution timeline between different solutions. By fusing all embedding partitions lookup into a single kernel, and by overlapping the local and the remote embedding lookups, we can significantly reduce the embedding lookup latency and efficiently support the fine-grained embedding table parallelism. And lastly, let me introduce our sparse overreduce optimization for the fine-grained embedding table data parallelism. In existing coarse-grained framework, the data parallelism is applied on the whole embedding table across all GPUs, and there will be an all-reduced communication on all embedding parameters. But due to the sparse and input-dependent nature of embedding table, not all embeddings are assessed and updated in each iteration. So this will lead to redundant communication. To optimize this, we propose a local aggregated sparse overreduce. We first compute the unique index within the input batches from all GPUs. Then we locally reduce the gradient into a buffer. The size of the buffer will be the number of unique index times the embedding dimension. And lastly, we perform a traditional ring-based dense overreduce on this aggregated gradient buffer. And this helps greatly reduce the amount of overreduced communication of data parallel embeddings. So here comes the evaluation. First, we evaluate the end-to-end training and inference performance of OPER in a single node setting. As you can see, OPER achieves 2.3 times and 4 times speed up on average in training and inference respectively. And it can be observed that OPER performs better when the number of GPU increase. And we also conduct a multi-node scaling test on embedding computation performance. On average, OPER achieves 2.8 times and 1.7 times improvement in embedding lookup and the training throughput. And this speed up in the multi-node setting is relatively lower than in the single node experiment. This is because rather than using collective communication to synchronize all the embeddings at once, OPER communicates the embedding in a fine-grained per embedding manner that may not be able to achieve the peak communication bandwidth of the internode connections. And we also conduct an ablation study on the optimality of the parallelism. We work on 3 major metrics: the memory consumption, the lookup computation, and the communication. And we compile OPER with 2 greedy parallelization strategies and 2 parallelism strategies used in the state-of-the-art DLRM framework. And it can be observed that OPER is the only one that achieves near optimal performance in all 3 aspects, which demonstrate the parallelism strategy searched by OPER is near optimal. And thank you for listening. For more details, please refer to our paper, and I'm happy to take any questions.